In this lecture, I'm going to talk about the ligand phosphine or PR3. It's a trivalent phosphorus. And before I do that, I will introduce you to the ligand map again because we have to understand the role of phosphorus ligands in the context of studying organometallic chemistry. They are very good supporting ligands. They are extremely good supporting ligands. Now, if I look at a ligand map, I can think of organometallic chemistry as being composed of those compounds which have a metal carbon bond, but there are several ligands which are supporting ligands, and many of them are non-carbon in nature. The metal is bonded to an element other than carbon. Let me now look at the whole class of carbon-based ligands. Those are listed in this cloud, which is shown here. If you compare it with those of the non-carbon ligands that support organometallics, you find that they are in fact a slightly smaller group, but among them, phosphorus-based ligands are extremely important. Phosphorus in the oxidation state 3 is extremely important. And we have already looked at nitrosyl ligands. These are ligands which are similar to carbonyl, but then because of the positive charge, they behave differently compared to carbon monoxide. Phosphorus in oxidation state 3 is naturally a good electron donor because it has a pair of electrons on the phosphorus which can be easily donated to the metal. And if you remember your periodic table, it's in the same group as nitrogen. And so this pair of electrons is not involved in bonding. Compared to nitrogen, in fact, the pair of electrons on phosphorus can be more readily donated. Secondly, the reaction of PX3 with RMgX, a Grignard reagent, will readily give you the ligand PR3. And this reaction can in fact be done stepwise. This reaction can be done stepwise. What is the advantage in doing it in a stepwise fashion? Very simply this. You can prepare PR2X, PXR2, and PR3. All of them are accessible. Another great advantage with phosphorus ligands is the fact that 31P is an NMR active nucleus, and so it can be used for recording NMR spectroscopy of the organometallic compound. And because organometallic compounds are mostly diamagnetic, the use of NMR is extremely valuable. It is an empirical tool, as I will shortly explain to you, but this is extremely valuable in characterizing an organometallic compound. The coordination to the metal usually shifts the ligand upfield, which means that you have lower delta values, but 31P signals can be shifted downfield also by close to plus 30 ppm. The dispersion, meaning the range of chemical shifts observed in phosphorus NMR, is much greater than what you observe in proton NMR. The effect of chelation is, however, very erratic in the case of phosphorus ligands. It depends on the ring size, and even then, it also depends on the metal. So, the moment you have a ligand which is diphosphine, bisphosphine, you can have chemical shifts which range from plus 20 to minus 20 ppm with respect to the free ligand. Now, if you look at the infrared spectra of metal carbonyls with phosphines, you realize that the phosphorus ligand is actually more stable when it is positioned in a cis-oid geometry. If I have two ligands, the trans complex is not the one which is formed first, it is the cis complex which is formed. We have already alluded to this when we have talked about the bonding tendency that is there in carbon monoxide, the tendency of the metal to have pi bonding with respect to carbon monoxide. So one way to explain this is to say that the phosphorus is a poorer pi accepting ligand compared to carbon monoxide, and that is the reason why the ligand is positioned in the cis-oid fashion when you have an octahedral complex. The CO stretching frequency is very often dependent on the trans ligand, and you find that the CO trans to the phosphine is in fact having a lower stretching frequency. This suggests that the phosphorus is in fact a poorer pi acceptor. A similar observation is made with respect to ligands which are there in MPX3 thrice, CO3 thrice. These are octahedral complexes which can be found in the FAC geometry and in the trans geometry, in the MER fashion. And you find that the FAC is in fact a more stable complex compared to the MER complex. Once again, all of these observations can be readily understood if you say that PR3 is in fact a poor pi acceptor compared to carbon monoxide. The lone pair is a good donor, and if you remember your bonding of PR3 or NR3, you know that the 3p and the 3s are valence orbitals. They are the ones which are combined to form bonding orbitals with the R group. And the lone pair is mostly a sp3 hybrid which is present on the phosphorus. But because as you go down the group, the separation between the S and P gets larger, the S can be less involved in bonding compared to the P. So this is what is changing as you go down the group, and you find that the phosphorus groups are more determined by the size of the R group. The phosphorus PR3 bond angles are determined more by the size of the R group and also by the hybridization tendencies. But the size of the R group makes a very big contribution to the PR3 angle. In other words, the RPR angle is dependent on the size of the R group. So where is this pi acceptor character coming from? If at all it is coming from the phosphorus, it has to come from the empty d orbital which is present on the phosphorus. This was a popular explanation for a long time, except that once theoretical calculations became popular, it was realized that the d orbitals on phosphorus are actually virtual orbitals, and they are too high in energy to reasonably interact with the metal filled orbitals. So if they're too high in energy, the gap between the metal donor orbital and the phosphorus acceptor orbital is very large, and so the interaction is going to be a poor interaction. From perturbation theory, we can say that this interaction is going to be insignificant and not contribute to the stabilization of the metal T2G set of orbitals in an octahedral symmetry. So let's take a look at the periodic table. Here we are. with phosphorus in the third row of the periodic table. If you consider hydrogen and helium as the first row, second row is the first row, what we call as the first row elements. The third row is the one which has the phosphorus in the nitrogen group. And you find that the d orbitals start getting occupied only when you come to scandium, titanium, vanadium, chromium. So that row gets started only after the noble gas argon is present at the end of the phosphorus group. So in other words, these d orbitals which we are talking about are present only after about 7 elements. So the possibility of phosphorus d orbitals being involved seems to be a bit remote if the calculations are correct. So the best way to probe pi acceptor character of a ligand is to look at the metal carbonyl complexes in which these ligands are present. So I have chosen for you the FAC complexes where there are 3 of these phosphorus ligands which are pitted against 3 carbon monoxide ligands in a trans geometry. That means each phosphorus is against another carbon monoxide in the trans geometry. And let's look at the carbon monoxide stretching frequencies as a function of the substituents on the phosphorus. When you have a phenyl group, the stretching frequency of the carbon monoxide is around 1934 centimeter minus 1. And when you change it to an ethyl group, then the stretching frequency goes up in value, which means that the stretching frequency of the carbon monoxide on the trans geometry is experiencing less electron density in the pi star. If I change it to OMe, where you have a methoxy group, then the stretching frequency even goes up in energy. So what you find is that as you increase the electron withdrawing capacity of the phosphorus ligand, as the electron withdrawing capacity of the groups on the phosphorus are increasing, the stretching frequency seems to be going up in value, which means less pi acceptor character of the CO is being manifested, which means the phosphorus ligand is also competing for the pi acceptor character. And that would be one way to understand why the stretching frequency is going up. If you have a very strong electron donor, for example, Di-N. Di-N is the ligand where you have 3 nitrogens coordinating to the MCO3 unit, the MCO3 Di-N complex. 3 nitrogens are there, 3 carbon monoxides are there. Then the stretching frequency has gone down all the way to 1898 centimeter minus 1. What this suggests is that carbon monoxide is now behaving as an extremely good pi acceptor when you have the very good donor Di-N. When you have 3 carbon monoxides pitted against the 3 carbon monoxides, the stretching frequency is 2000 centimeter minus 1. So in other words, as I increase the pi acceptor character of the phosphorus ligand, as I increase the pi acceptor character on the phosphorus ligand, the stretching frequency of carbon monoxide is going up in the transposition. So this can be better visualized in a graphical form. Here I have in a graph the plot of the 2 stretching frequencies that you observe for FAC complexes, the symmetric stretch and the asymmetric stretch. And you find that the symmetric stretch parallels the way in which the asymmetric stretch changes. So you can take any one of the series and look at the way the frequency is changing as a function of the substituents on the phosphorus ligand. And for comparison, we have put acetonitrile, which is also as a good donor, not a very good pi acceptor against the carbon monoxide. So tris acetonitrile MoCO3 is the second point which is present here. This is tris acetonitrile, tris MoCO3. This one is for diene. Diene is the ligand which is pictured here. This is the ligand diene, which is a very good donor. This is a very good donor, and what it does is it lowers the stretching frequency of the trans carbon monoxide, which suggests that if you do not have a pi acceptor trans to the carbon monoxide is capable of accepting a lot of electron density, and so the frequency of CO goes down all the way to 1750 centimeter minus 1. Now, as you make the trans ligand a poorer donor or a better pi acceptor, the frequency goes up in energy. The frequency keeps increasing as you improve the pi accepting character of the trans ligand, or you decrease the donor capacity of the trans ligand. So here both of the stretching frequencies, symmetric stretching frequency and asymmetric stretching frequency, change in the same fashion and are very clearly suggesting that if you have a methoxy group or an ethoxy group, the trans carbonyl stretching frequency keeps increasing, which means there is less and less pi star electron density on the carbon monoxide. That means the trans ligand is a poorer donor, or it is a weak pi acceptor which is increasing more electron density. If I have a methoxy group compared to an ethyl group, then the methoxy group is electron withdrawing, and it will pull the electron density on the phosphorus towards itself, and it will pull all the orbital energies down. It will pull the s orbital, the p orbital, and the d orbital energies down. If the d orbital energy comes down, then the phosphorus ligand becomes a better pi acceptor. So POMe3 is a better pi acceptor compared to PET3, and PET3 is better than PPH3, and so on and so forth. So that is what this set of complexes seem to indicate through this trend that you observe in carbonyl stretching frequencies. Now let us look at what the theoretical chemists or the computational chemists are telling us. They are telling us that the 3s and 3p orbitals on phosphorus are valence orbitals. The d orbitals on phosphorus, well, they are very high-lying virtual orbitals, and because they are virtual and because the gap between the 3p and the 3d is very large, it is unlikely that the d orbitals are involved in any bonding. There is another added complication to this whole story, and that is the measurement of empty orbitals is measurement of the energy levels of the empty orbitals is virtually impossible. So when this theory that the d orbital energy levels are very high and that it is not possible to measure their energy levels properly, an alternative explanation became popular, and that was what was called the sigma only explanation for the bonding between phosphorus and the metal. The decrease in the nu CO, or the carbonyl stretching frequency, which is trans to the phosphorus, is proportional to the electron density on the metal atom, which in turn is affected by the electron donation from the phosphorus ligand to the metal atom. If Py3 is a very good donor, then metal has greater electron density. If there is greater electron density on the metal, then the carbonyl stretching frequency is decreased by population of the pi star orbitals on the carbon monoxide. On the other hand, if Py3 is a weak sigma donor, then the new CO is higher. The stretching frequency is higher because there is very little electron density on the pi star orbital. So with POET thrice, for example, one can say that the sigma donation is poor. And because the sigma donation is poor, then the electron density on the pi star orbital is correspondingly affected. It's not getting populated, and so the frequency is high. Now let us take a look at the measurement of the donor capacity of a phosphorus. If this is in fact true, we can get an idea about the donor capacity of a phosphorus ligand by measuring its ionization potential, the energy required to pull out an electron from the pair of electrons that is available on the phosphorus would be indicative of how easy it is to donate electron density from the phosphorus to the metal. Another option is to look at the tendency of the phosphorus ligand to get protonated, which is very similar to donation of electron density to a metal empty orbital. Now the empty orbital is provided by the proton. That's the only difference. So you can measure the pKa of the phosphorus ligand and indirectly get a measure of the tendency of the phosphorus ligand to donate electron density. You can also measure in solution, you can measure the E half or the oxidation potential of the phosphorus ligand. Ionization potential is often done in the gas phase, and E half can be measured in solution. So these are three ways by which we can measure the donor capacity of any ligand, let alone the phosphorus 3 ligand that we are talking about. Any ligand can be uh, assessed for its donor capacity using these three metrics or these three parameters. Now here I have for you three ionization potentials, and you can immediately see that they fall in the range that you would expect based on the electronegativity of the group attached to the phosphorus. When a butyl group is attached to the phosphorus electron is easily removed. The ionization potential is 8 electron volts. Whereas when I put a phenyl group, which is a stronger electron withdrawing group and a poorer donor, then it is slightly going up to 8.2 electron volts. If I have PF3, which is a very strong electron withdrawing group, the fluorine is an electron withdrawing group, then PF3 turns out to be a poor donor. The ionization potential is much higher. It is close to 13 electron volts. So as you increase the ionization potential, the donor ability of the ligand appears to come down. So this is a trend that we would expect intuitively, and it seems to fall in the same trend in the, if you remember your graph, you will find that this is the order in which they are found. So let us now look at a second measure of the basicity of phosphines, second measure of the donor capacity of the phosphines. If the donor capacity is very good, then in the equation that is shown here, that is the phosphorus, protonated phosphorus dissociating to give you the free phosphine and the H plus, this equation will lie, if there's a very good donor, this equation, this equilibrium will lie almost on the left side. That means PR3H plus would be very stable. PR3H plus would be very stable, and PR3 would be very less in solution when you have a very good base. The Ka will be small, and correspondingly pKa will be very large. So when the pKa is large, it means it is a good base and the dissociation is very poor. In the pKa is small, that means the dissociation is very good and the amount of H plus is very large. And so if the dissociation is large, then it is not a good base, it's a poor donor. So you find that as you put electron withdrawing groups on the phosphorus, as the number of withdrawing groups increase on the phosphorus, the pKa value is going down. So PBU3 has got a value of 8.43, whereas R2, PR2, PPH2, OMe, which has got one electron withdrawing group, the value has dropped to 2.69. So if I have a chlorine in the para position of the phenyl group, then it becomes a very poor base. So you can see that if I have a poor ligand, then the pKa value is small. So this is one method of measuring the donor capacity of the phosphine. And this is also falling in the trend that we kind of expect. And it seems to be a good measure of the ability of the phosphine to attach itself to a proton. Now, the sigma donor only explanation suggests that there are no pi effects at all. And if px3 is a weak sigma donor, then the electron density on the pi star of the trans carbon monoxide is less, and so the frequency is high. The carbon monoxide stretching frequency is high. And this seems to explain most of the values that you observe. Is there anything else that we would expect from this explanation? If you have a poor donor, then the PM bond should be weak. If the PM bond is weak, then the PM bond should be weaker. And you should have longer PM bonds. The weaker bonds will lead to a small dissociation energy. Delta H for that bond should also be small, and the bond length should also be large. So let us take a look at the bond distances. Sigma donor only explanation predicts that you would have, when you have very strong electron withdrawing groups on the phosphorus, you have a poor donor, so the PCR bond should actually be longer. And the CCR bond, which is the trans carbon monoxide bonding that we're talking about, that should be shorter. So you expect correspondingly for a slightly better donor, PPH3, you expect a shorter bond on the phosphorus chromium side and a longer chromium carbon bond on the trans side. So this is what you expect based on the sigma only explanation, or rather, if the phosphorus has no pi acceptor capacity and it is only the sigma donation that is determining the bond strength, this is what we will expect for two sets of ligands. So although we can compare a lot of these complexes, I am just showing for you one set of complexes, and you can refer to the paper for more examples. What you find is that the bond distances are not in the expected trend, not having the expected trend. So in other words, in PPH3, you expected to have a shorter bond. And what you find is what is listed here. You have a shorter bond when you have the so-called weak POR3 attached to the metal atom. So phosphorus chromium bond is shorter than the phosphorus chromium bond for PPH3. And this is exactly opposite of what the sigma only explanation would predict. If phosphorus is only a sigma donor, you would expect the trends to be in a different way. And that's what is struck off on this slide. And that's what you expected for the sigma donor only explanation. So we can categorically say that the no pi bond theory, okay, so if the theory says that there is no pi bond, that theory has failed. If that is the case, then you would have expected the bond distances to be in a different way. And now we see from the experimental bond distances of several phosphorus compounds that the strong electron withdrawing group present on the phosphorus in fact shortens the PCR bond. So this seems to suggest that there are in fact distances which are consistent with the presence of pi bonds. So pi bonds are present, pi bonds are definitely present on these compounds. So we are going to examine this theory of no pi bonds are there in phosphine complexes. If there is no pi bond, there is only a sigma bond that is involved between the phosphorus and the metal, then only sigma Fx should be operative. And if there is a very good sigma donor ligand, the metal ligand bond should be short and it should be strong. So on the left side of the screen, you find the platinum 2 complex. Platinum 2 is a D8 system and so forms nice square planar complexes which are 16 electron complexes. In the 16 electron complex, two phosphines are there, but the two phosphines are having different substituents on the phosphorus. In one case, there is a CF3 group, and the presence of a CF3 group, which is electron withdrawing, would make the phosphorus to be a weak sigma donor. So the weak sigma donor, which is having two CF3 units, is having a bond distance of 2.17 angstroms. So I'm going to mark this 2.17 angstroms is this bond distance that we are looking at. And the phosphorus, which is having a PPH2 group, is having a bond distance of 2.24 angstroms. Okay, so this is not consistent with the fact that sigma donor effects are the most important effects and the only effects that are operating in this complex. So you would have expected the good sigma donor, which is PPH2, to have a shorter bond distance, and the poor sigma donor, which is PCF3 substituted ligand, that should have a longer bond distance. Exactly the opposite is found. So that is one reason why we believe that the sigma only explanation is not correct and there must be a pi bond involved. So this no pi bond theory is false. You take a look at the rhodium complex, which is also a D8 system. Rhodium is now a 16 electron species here, and in this complex you have two phosphines which are trans to each other, the same ligand PPH3 on either side, but one phosphine is having a good pi donor in a transposition. This is having a good pi donor in the transposition, and so if there is a pi bond involved, using the same arguments that we used to explain carbon monoxide stretching frequencies when they are trans to chlorine, we would expect a similar effect to operate. In other words, the pi donation from chlorine to the rhodium should in turn promote pi donation from rhodium to PPH3 if there is a pi bond between the rhodium and the PPH3. And if this is indeed operative, you would expect a shorter bond distance between the PPH3 and the rhodium when it is trans to a chlorine. On the other hand, when two PPH3s are trans to each other, as in the case of the phosphines which are encircled in blue, so these are two phosphines which are trans to each other and they do not have a pi donor which is on the trans side, then the bond distance in fact is longer. Why? Because on both sides you have only pi acceptors. Now we have to look at all the factors that we have considered and find out whether the pi bond theory will fit. When X is electron withdrawing, it causes the 3d orbital to become lower in energy, contract, and thus it makes a px3 a good pi acceptor. But what do we do with the computational result, which seems to suggest that the d orbital is too high in energy? Is there any other orbital on phosphorus which has the right symmetry and energy to accept electron density into the ligand from the metal? This is what we have to consider when we talk about the pi bond theory. If the computational chemists and computational studies are right, then the d orbital is too high in an energy and it cannot be involved in bonding. On the other hand, all the other factors that we have talked about experimentally point to the fact that if it is only sigma bonding, the observations cannot be accommodated. There seems to be a pi bond between the phosphorus and the metal. Very clearly, there is something other than d orbitals on phosphorus to make it a pi acceptor or a pi acid. Now, this was shown to be negative hyperconjugation or donation of filled, filled orbitals on the metal, donating electron density to the sigma star orbital of the px bond. The sigma star orbitals on phosphorus then are low enough in energy to accept electron density into them, and as a result it can function like the d orbital and behave like a pi acceptor. Now the question is, what is their shape? Is the shape of the sigma star orbital on the px3 ligand, is that similar to the d orbital on the phosphorus, or is the symmetry suitable for accepting electron density into the sigma star orbital?